There we go. Okay. Tonight I'm going to do Intro to Niagara. I'm Ken Brueck. A little bit about me. I've been tinkering with Unreal for about a decade now, professionally for about 8 years. My very first project was something called Foos. It was like a mixture of physical foosball with an arcade game. It was pretty cool. I was awarded an Epic Mega Grant for it, which only covered licensing fees at the time, so it wasn't a very useful Mega Grant. By day, I run a company called Modus VR. It's another Unreal-based tool. It's geared towards audio-video companies to help them communicate their vision so they can quickly throw together a project, design a space, and articulate their vision by putting in AV equipment, helping people see what it is. My side project is Dirty Dirty Pirates, just released on Steam last month, and it's a lot of fun. It's really good. Guess we could do a post-mortem on that sometime. All right, but Niagara, what is Niagara? So Epic describes it as the visual effects system in Unreal. At the end of the day, it's a particle system, but it is a really cool particle system. Just by show of hands, who in here uses Unreal or has used Unreal? One. Awesome. Okay. So Niagara is crazy complicated. It exposes everything to you. It supports these massive complex workflows, which is both good and bad. It can be really overwhelming to get started. Really, the best way to do that is just to open up stuff and pull it apart, because there is a severe lack of quality documentation from Epic's part. There's like thousands of things you can do, and maybe 20 are documented. So the fundamentals of a particle system are going to carry over to a lot of applications. This isn't unique to Unreal, but this is a good foundation as we're talking about stuff. So at the core of a particle system is the particle. So this is typically the thing that you see. And there are often many, many of these things. So that might be a single spark, a single flame, a single puff of smoke. But the important parts about a particle are, one, that they have behavior. So that might be physics. That might be collisions. It can also be custom behavior. You could have a particle have a mood, and as it gets angrier, it turns more red and vibrates more. They also have a renderer. So again, since this is something that's visualized, that might be a sprite, which is just a simple 2D image that's typically always facing the camera. It could be a 3D model. It could be a ribbon. It could be a light. There's a lot of different things it could be. And then particles have a lifespan. Typically, they die eventually. Sometimes it's really quick. Sometimes it's longer. We'll get back to that in a minute. And then the most important part as far as Niagara is concerned is particles can store data and do math. And so that's where a lot of the power comes from. Now, the next level here is emitters. So an emitter, its job is to spawn particles. That's all they do. So you might have a sparks emitter, and it's going to shoot out lots of sparks. You might have a smoke plume emitter that's constantly shooting out lots of those smoke particles. Emitters can be looped, or they can fire once. So think about a firework, right? That would just pop and burst once, compared to a hose, where it might be a constant flow of particles. Emitters, it's also their job to determine the initial state and location of particles. You might say, okay, well, we want to start off this particle's journey in life over here, and this other particle may be over here. Finally, you have a system, which is a collection of emitters. So a system is typically the thing that you're working with at runtime. So if you're building a campsite, you would probably have a campfire system. And this campfire system would have a flames emitter shooting out flame particles. It would have a sparks emitter shooting out spark particles. And it would have a smoke emitter shooting out smoke particles. And so that also, just like emitters and particles, can store data and do math on them. And so you basically just have any point in the system, you can start adding your own logic to do lots of cool things. Yeah, go ahead. No. So you can, typically there'd be different things. sometimes an emitter can spawn multiple particles using different renderers, but the logic for the particles are the same. And that weird, vague statement will make more sense in a minute, but usually you want them distinct. And yes, yeah, so it's not even possible. But a lot of that is so that you can reuse emitters. So let's say you've got a really great spark particle that looks awesome, and then you've got a really good behavior for emitting them. You could then reuse that emitter in multiple systems. So you could say, all right, well, I've got my tiny fireplace here, maybe even a match as another emitter, and you might have a big explosion as a third emitter. And all of those emitters can be driven by data. So you could have like a variable that drives the intensity and quantity of sparks. So you can reuse that emitter in tons of different places, which is part of what makes Niagara so powerful and large team friendly. It's also what makes it kind of complicated and overwhelming, which is like the duality of everything in Niagara. So for tonight, I thought it would be fun, laptop battery permitting, for us to recreate a really old effect from, I think it's Quake 2, the railgun. There's just some things I loved about this. And so Niagara can do some really advanced stuff, way beyond like sparks and things, but I thought this would be a really good starting point because it exposes us to a lot of different aspects of Niagara. But when I first saw this as a kid, I was just like enchanted by that little spiral effect when it shoots. I just thought that was the coolest thing. And it's actually not that hard to build, so I thought we would do that tonight. And when I close my laptop, it looks like, oh mercy. We're not used to that resolution over here. Okay. All right, so I'll pull up this project and, oh, we're doing good on battery. This project, I've got a couple other particle systems that I've built for different projects and stuff that I'll show really quick, and then we'll just kind of jump right into rebuilding that cool railgun effect. What I'm not going to do tonight is I'm not going to focus on making sure this is performant. I don't care about performance right now. That's something we dial in later. I'm also not going to spend time going into anything outside of Niagara. We'll spend just 1 minute on it, but I really want the bulk of it to be on Niagara. Mostly because once I started tinkering with Niagara, I found there was such a drought of good, useful information on how to get started that I really wanted to hit those points hard. Okay, so let's close that too, get us just a little bit more battery life. Okay. So let's just show you some of these things really quick. So this is a simple system I put together for Modus VR. This was visualizing speaker coverage patterns. So you can toss a speaker in a room and you can kind of see what it does. This was a fun effect. We're actually doing all sorts of different things in here. Here's another interesting little effect. This one is really material driven more than anything else. As far as particle systems goes, it's pretty simple and straightforward. Then over here we get to Dirty Dirty Pirates. And this was a really fun effect, though we're missing some things here and I don't know why. This little plague ball, there's a game mode where there's, just like the real plague, it floated around as a giant ball and attacked people one at a time. It's actually not how the plague worked, in case anyone's curious. And so this was this is a single system made of a ton of emitters. So in this case, we have the rats that are shooting off, we have the goop that's shooting off, we have these little balls of pus that are kind of bubbling around, we have the orb in the middle that's kind of doing its thing. And that all comes together as one emitter, or one system. So when it's time to spawn it, I just bring in this one asset. Even the goop splashes on the ground are all part of that same system. And then those are all reusable pieces. Let's see here. Let me try resetting this guy. Those pieces are all reusable. And then in another similar system, I'm reusing a lot of those pieces on the character, so that then we can have the rats and boils sampling points on that 3D model and having them spawn there. So it was a really handy way. I spent a lot of time investing in the effect, the rat animation, and everything. And then it continued to pay dividends for when a character was infected. So super gross and wonderful. Okay, so I'll do a quick preview of what the effect is going to be like that we're hoping to build tonight. So you pick up the gun and you shoot the railgun. So this one is doing a little bit more than the one we saw in Quake. It lights things up even, but it still has that little spiral that I thought was so cool, but it does a lot more. Especially it has like muzzle flash that I thought added a little bit of impact. So that's what we're going to build. So first things first, to start a new Niagara system, you just right-click in the content browser and click Niagara system. And this is your first exposure to where Niagara makes everything complicated. Instead of just having a new one, it asks you all these different options. And that was something that Epic added a couple versions in because people were having such a hard time getting started that they then made it easier to just copy existing systems. So that kind of shows where the challenges were straight from the beginning. So we'll start with an existing one, and I'm going to use a fountain, not because it's a great starting point, but because it'll give us something to work with. And I'm just going to call this Railgun Demo. Now, before we go too much further, I'm going to jump into where we're actually spawning this particle system. And I don't want to spend time looking at how this is set up so much, other than there's two important things here. In Blueprint, we are spawning the system attached. So you basically have two options when you spawn a Niagara system. You can spawn one in the world, and it'll just live at that spot, or you can spawn it attached to something. So this is spawning it attached to the weapon, specifically right at the barrel of the gun. That's going to be important as we have like a smoke effect coming out of the gun. As the gun moves, we want that particle system to move with it. And then we're setting a float parameter. So a float is just a number, and the parameter name is length. One of the cool things about Niagara is you can pass data in regardless of whether or not the Niagara system is expecting it. So even though I'm using this Railgun Demo system, it has not been set up to accept a length variable, but we're going to use that in a little bit. But being able to just do this whenever I want decouples my system from data input, so I can swap stuff more easily and it will just ignore data it doesn't need. So really quick then, now that we've swapped out the particle system, I'm going to show you what happens when we fire. It's spawning that system attached, and it's just doing this weird fountain effect that just shoots balls in the air. But this particle system never dies. So that's going to be an important piece that we come and talk about later. Now, every time I click, it's going to spawn a new one. So if I click this a lot, we get an absurd, just a stupid looking gun, an absurd amount of particles, and it will never end. And if I continue to click, I'll eventually crash the application because, you know, like it's just unlimited. So that lifespan, the looping behavior is really important. Okay, so this is, oh goodness, this is going to be so cramped. This is the interface for working with Niagara. So this is the Niagara system that Unreal provided by default. We won't go too much into the UI here just because there's so much. But the main area we spend our time in here is in this node graph. And right now we have two nodes. We have one for the system. So we'll only ever have one of these blue nodes in here. And then this orange one is for the emitter. And so by the end, we'll have several, if things go well, we'll have several Niagara emitters inside this system. And they all kind of just do their own thing under the umbrella of the system. Okay, so first things first, on these nodes, you'll notice a few things. We have these groups here. So in fact, on the emitter, it shows it better. Emitter update, particle spawn, particle update. And then inside each group are modules. Modules are where all the logic happens. Groups are just a way of organizing them. So nothing actually happens on a group. So in the system here, the most important one we care about is system state and this inactive response and loop behavior. So the entire system will loop. All right, so if we have emitters that only fire once, if the whole system is looping, it's going to fire every emitter on that cycle. But since we're doing a single shot poof, we want the railgun to shoot out, and then die, we're going to set this to once. Loop duration doesn't matter too much, but inactive response does matter. So there's two options here. Basically, the two options allow you to control who's in charge. So if you say inactive response is complete, let emitters finish, that's basically going to say we're going to let all the particles finish, all the emitters finish, and when they're done, I'm going to self-destruct, and it'll clean up myself. So that way, when you're firing a gun, poof, it spawns the Niagra system, everything runs, and then it cleans itself up, and you're safe. Hopefully, right? Hopefully it doesn't crash. Emitters have a similar thing. So if we come to emitter state, you'll notice it also has an inactive response, but it is worded slightly different. It says, let particles finish, then kill emitter, or kill immediately, or continue. Basically, do we want to let the emitter just shut off the valve and destroy every particle immediately? Or do we want to let those particles live out their lifetime, and when there are no more particles, then the emitter can die, at which point then the system can die? Clear as mud so far? Okay. We don't worry too much about that. The main thing, though, is we don't want this to loop either. So what we're going to do, we're going to start off making that little blast, a little poof, the nuzzle flash, I guess, but we're going to make it look a little bit more interesting. I'm going to rename this and call it nuzzle flash. And we'll take a look at some of these modules. So the emitter is going to run once, and it's going to last for 2 seconds before it'll stop. And we could change that. We can make it longer. But right now we have a spawn rate of 90. So that means for the 2 seconds that this emitter is alive, it's going to be spawning 90 particles per second. And so, I mean, if we just crank this up to 500, you can immediately see the difference. But think of it still like a hose. It's open for 2 seconds and then closed. And the spawn rate is how many particles are coming through. But for a muzzle flash, we don't really want that. We want it to be instant. So I'm going to disable this. So you can, at any point, you can just disable a module by clicking that checkbox. And we're going to do spawn burst instantaneous. So instead of it being a rate, it's going to fire a whole bunch all at once. Right now, it's firing one particle every time the emitter loops, so every 2 seconds. We're going to bring that up to like 3, that might be too much. We'll do 150. And so now we get more of a firework effect. It is a burst of particles. And the only reason, by the way, this whole thing is looping is because we're in the editor. If we were to bring this into the world now and play it, it just does what we expect. It only fires once, and it is cleaning up after itself, we assume. I promise it is. Okay, so that's the emitter update. The next thing is particle spawn. This is the next group. So particle spawn, anything in here is going to be run on every single particle. So if you have 1 million particles, each of these steps are going to be run 1 million times. But that's what makes particle systems so cool, is they have a lot of this behavior. So under initialize particle, we've got a bunch of just simple setup stuff. So you can set the lifetime of that particle. And in this case, you're able to look at a random value. So right now, these particles will live between 1.4 seconds and 1.75 seconds. So when that particle is spawned, it's going to randomly pick a value in between those two numbers, and then that lifetime is going to be set on that particle. That data lives there, and after whatever value it's set is finished, the particle will die. We can also set the particle's color, and I'll expand this a little bit more so they're on the same row. So this is just simple RGB values. When I change that to red, you see the particle turn red. We won't worry about mass for now. But then we can do sprite size. I'm going to change the sprite size to something non-uniform. So uniform basically means it'll be a perfect circle. Non-uniform means we can distort it. And I want this to be more like a spark. And a spark is usually a little bit longer, or at least it looks longer as it's moving. So we'll make this maybe 1 tall by 6 wide. Let's see if we can zoom in there. There we go. It's kind of hard to see, but I promise they look better. The problem, though, let's see if I can, there we go. The problem with these particles is they're kind of aligned any which way they want. They're facing the camera. These are 2D sprites, but they're kind of rotated randomly. But a spark really moves, it's angled in the direction that it's moving. And really The only reason sparks look long is because of motion blur, but we won't worry too much about that. So this is the one exception to where we don't follow top to bottom. All of a sudden we jump to the bottom here where we're describing the renderer. And so these sprites are defaulted at, or these renders, or these particles are sprites. We can change those characteristics. We don't worry about much of these other than alignment. And we're going to change that to velocity aligned. And now when these sparks move, as they go up and then down, they're going to point in that direction. So they get a much more natural look to them. Let's see if I can make this preview a little bit bigger. Does that show up well enough? I guess so, sort of. Okay. All right. That's pretty good on initialized particle. The next one is shape location. So this is just a module that was brought in. If we want to look at the code for it, we can double click any module, even the engine provided ones, and see all of the shader code that came into that. It's a lot. We won't worry about it too much, but shape location basically says, okay, where do we want these particles to start their life? In this particular case, this fountain emitter defaulted to a sphere. And so you can define the sphere, so we could crank that up and they all start much farther apart. Since we want this to emit from the end of the barrel of the gun, we want this to be a pretty small radius. And all the units in Unreal are in metric. So this is 2 centimeter radius, so about a 4-inch barrel, or 4 centimeter barrel. Okay. And then add velocity. This is the last one. So basically the emitter is saying, okay, when this particle starts its life, does it have any velocity in it to begin with? And it does, but it's not quite doing what we want. It's shooting upwards. So in Unreal, their coordinate system is x plus is forward and z is up, which is why when we look at the cone axis, so basically we've decided to add velocity in the shape of a cone. It's picking a random value, which I want to dial down a little bit here. And then it's saying, okay, well, which direction are we adding velocity? So right now it's adding velocity straight up, but we want it to be forward. So we're going to change that to x is 1, 0 is, or z is 0. So now it's going to shoot forward, but they immediately fall. I don't want them to fall. I want this to be like a cool electric looking thing. So then that brings us to the last group, which is particle update. And this is code that's going to run on every single frame. So every time the engine draws a new frame, updates the screen, it's going to run this code on every single particle. And so the easiest way to solve this is to disable gravity force, and we'll keep drag. So drag is basically just resistance against velocity. So air, something moving through air is going to hit drag, and it's going to slow down unless it's self-propelled. These just have, if we wanted, we could have velocity be added at the particle state, and it would continually thrust it forward like an airplane, but we're only adding velocity at the beginning of the particle's life. So it gets that initial push, and then every frame after that, it's hitting drag, and it's slowing down. So we'll keep drag up there. And that looks okay. So as we play this, they just kind of shoot out. So it almost looks like a flat cannon type of weapon. But that's not what we want. We want it to look more interesting. So to do that, we're going to add another force. We're going to add curl noise force. So curl noise is just kind of like it's a vector field. So basically think of it like a Perlin noise type of a thing, whereas it's an invisible force that's going to cause particles to move almost in random directions, but it's not per particle, it's in groups of particles. So you'll see collection of particles move along this. We have frequency over here. The higher the frequency, the more times those particles are going to change direction. And the greater the strength, the more influence that vector field is going to have. So if we start cranking this up, and then cranking up the frequency here, we'll start to see the particles do kind of like a fun little dance. So watch what happens now when we play. I don't know if you can see that, but they kind of squirrel around. It was just that one little curl noise. We're going to use that a lot. I love curl noise. One other thing here, though. So at the very beginning, when we initialize color, we're going to use the same color in multiple places. And so this is a good time to introduce user parameters. So user parameters are just variables. You can define floats, colors, whatever you want to reuse throughout the system or even be driven at runtime. So earlier on, we had a length variable, and I'm just going to add this now. We'll come back to that later. And I'm also going to add a color variable. And so now if I want to use this color variable, and I'll set this to something I want better, I can drag this variable, hopefully, and you'll see all of these different slots activate, indicating, hey, yeah, we can accept this variable. So now that I put the color variable there, it shows up. Yeah, go ahead. Yes, yes. So, oh boy. Yeah, so, and this is actually one of the areas where Niagra is pretty phenomenal, but also it can start to hurt you. So let's say for lifetime max, we wanted something a little bit more involved than just a static number. We can click this little arrow here, and all of a sudden we can start doing quite a bit of math in there. So we could do a simple multiply float. So the maximum now could be driven by our length variable, and maybe length is going to vary. But you can keep stacking these. You could, like, it gets unreadable really quick. Like this much right now, if you were to come back tomorrow and look at it, and I'd be like, I have no idea what this does. It's almost as bad as regular expression. When I'm dragging color, it'll let me bring this over a float, and then it lets me, so it accepts the color. It basically auto-created a make float from linear color. So it says, okay, I'll accept a color, and then you tell me which of the 4 channels do you want to sample. But then I could turn one of those channels into a multiply, and then I could have that sample something, and it just gets real ugly real fast, but it's so powerful. It's so powerful, and it's so accessible. It used to be before Niagra, the previous particle system in Unreal, in order to do just that, you had to write your own engine code. Like, the barrier of entry was just stupid high. So this is incredible, and there is a better way to do complex math like that. But I'm glad you asked, because that was a really good point. Okay, so I'm just going to assume that we're super thrilled with how that turned out. Next thing I want to do, let's see, how are we on time? Like, what time is it's 7 till? Does anybody else want that? That's the question. Okay. Well, we've got to do one other thing first before we do the spiral, and that's we're going to do a line. So we've got the muzzle flash, but I really want like a single line that kind of shows the path of the rail. And to do this, we're going to use a different type of renderer. We're not going to use a sprite renderer, and we're also going to get a little nitty-gritty with controlling things. So I'm actually just going to duplicate this, even though most of it doesn't make sense. And then you can click this little person here to isolate this emitter. So if you have a really complex system with a lot of emitters, you can click that and it'll turn everything off except for this one emitter. It makes it a lot more digestible to work with. Okay, so a ribbon particle, this is kind of fun. So a ribbon particle basically takes all of your particle positions and it will draw a nice curvy line through them all. It's super cool. When you add it to a bunch of particles like this, you just get it kind of like this pig pen effect from Peanuts. Like, it's just these random things. The cool thing, though, is Unreal gives you a lot of options for controlling which particles connect together and stuff. And it's like, when you're dealing with hundreds or thousands or millions of particles, it becomes quite the challenge to deal with. But like, that's super cool just in itself. Like, I just made a line cloud. All we need for that line is 2 particles. So we're going to keep a lot of this in here. We're going to keep our spawn burst instantaneous, but instead of it being 150, it's going to be 2. It's a really dramatic one. We don't want any velocity. We don't want any noise. We don't want any drag. Scale color, by the way, is just fading out the color over time. So we're not going to worry about that. Shape location, we're not going to worry about. But we're actually going to create our own module for this. And so if you think about what a module does, it does three things. It can read data, it can manipulate data, and it can save data. And that's all the module does. So when we have this shape location, it's saying, okay, great. It doesn't even really read much in that case. I mean, it reads all of these inputs, but outside of that, it says, okay, great. We're going to generate some math to figure out where a random location in a sphere would go, and then we're going to write it out to the particle position. And that's all it's doing. I mean, there was a lot of code there, but conceptually, it's quite simple. Modules, just like everything else, you can reuse them across the board. We're not going to worry about that. So we're going to do what's called a scratch module, new scratch module. That basically says, let's create our own module, but we're going to do it within the context of this system. We're not going to have this be reusable by anything else, but any emitter in the system can use this module. And here we have a couple important nodes. Map get. That is Unreal's way of saying, here's how you access data. So that might be data that lives anywhere. That might be data that lives on the system, the emitter, or the particle, and a few other places. And a map set does the opposite. That's where you set the data. We don't actually need a map get for this. Every time a particle is spawned, it's given a unique identifier. So if we're only spawning 2 particles, we're going to have 2 IDs, 0 and 1. So it's, and that is hidden under execution index, not documented anywhere, of course. So if the execution index is 0, we know it's our first particle. If the execution index is 1, it's going to be our second particle. And that's amazing. Oh, we actually will use map get. Okay, so to grab data, we click map get, and then we tell it what kind of data we want. We want a float. What we're going to look for is the length. So every time we have this gun here, and I had set this up earlier, but we were doing, when we spawn the particle system, right before that we do, it's called a line trace. I can't remember what it's called in Unity, but it's line something. And basically we're figuring out how far the distance is from the gun until it hits something. And then we're passing that length into the system, and we're setting it as this variable length, which will be important here now. All right, so on this module, we're having an input length. So this is on the module, it's going to expose that as a value that we can put in, and later we're going to send our length variable to it. Now, if we just multiply these two, length times execution index, the first particle is 0, so it will have no length. It'll be right at the end of the barrel of the gun, and then the second particle will be all the way at the very end of whatever it hit. So it's super simple. That gives us our length, but now we need to turn this into a 3D coordinate. So we're going to make a vector. Again, x is the forward direction in Unreal Engine. So first particle is going to be right here. Next one's going to be at x equals 500 or whatever. We need to do one thing that, for the sake of time, I'm not going to explain too much. But we're going to, whoops, not location. It's position. We're going to now set particles position. So I could, if I wanted, I could set any kind of data I want. It could be mood, right? It could be made up, but there are lots of variables that already exist. One of those is particle position. I'm going to toss in this. There's a little conversion here between a true vector and position in Unreal Engine. It has to do with large world coordinates. We won't worry about it now. This will not work. There's one other thing we need to do. And that is we need to transform. So right now, everything we're doing is in local space relative to the particle system. Or when we're saying x equals 500, that's only in the system. Like, so it'll look good here, but once we get on the real world and we turn, it's going to shoot that way because it's always going to be x forward. So we need to just convert that from world to, or from local to simulation, and that'll do the trick for us. Okay, so now when we apply this, we don't see anything, which is exactly what we were hoping for. Let's see here. Let's make this a lot bigger. Okay, we've got one. We're missing our second. That's unfortunate. All right, it just means I missed something. We're spawning 2 particles. Oh, right. Input length is 0. So both particles are there. They're just exactly on top of each other. So I'm going to bring in our length variable. And now, hey, yay, that worked. And so in this case, this is where we're using 2 different renderers in the same emitter. We're using a sprite renderer, which gives us the balls. And then we're using a ribbon renderer, which gives us the line in between them. So we can have the same particles visualized in different ways, but it still is the same behavior. I can't have the start of the ribbon particle be over here and the first particle be over here, first circular particle, because it's the same particle. They're just being visualized 2 different ways. So I'm going to turn off sprite renderer, and now we get our sweet, sweet line. I don't want this to be using our color. I just want this to be white. And so then if we unsolo this and play, we'll get progress. Okay. All right. Then we'll do the spiral, and then we'll read the room and see if we want to be done. I'm also going to reduce the number of particles on that initial blast. Okay. To draw a spiral, we're going to take the same concept and go a little bit further with it. So instead of just having 0 and 1 particles at the very end, we're actually going to spawn a particle every single step of the way. We'll do every single centimeter just because that'll be the simplest math. And I should be renaming these. That would be a mature thing to do here. Okay, so since we're going to spawn 1 particle for every centimeter, then we can take our emitter state, or our spawn burst instantaneous, and just drag length into spawn count. And it's going to convert an int, or convert a float into an int, but now it's going to spawn 500 particles. Our logic is going to be all wrong, though, because right now we're saying take the length and multiply it by the particle index. So that means at 500, we're going to have particles way out there. We don't want that. That's not what we want at all. So I'm going to delete that module, and we're going to create a new Scratch module. This is where stuff gets kind of cool. All right, so execution index, again, 0 through now 500. We're doing that length. So I have another input here, input length. Okay, so we're gonna, see, I might steal some of this code from the previous one because it's great. By the way, you can also have multiple map set and get nodes for your more complicated stuff. That's often what you end up doing. Okay, so this time we're not going to multiply execution index by anything. That's just going to be our X location. But for our, oh, we don't need input length, but we do need radius. Some quick trig will tell us to draw a circle, we need sine and cosine. And the great part about this is it doesn't even matter which we do for X or Y because we're just doing a circle. So we can get it wrong and it doesn't even matter. Okay. Now, if we, oh, and then we have our radius. So if you take sine of degrees, cosine of degrees, that's going to give you an XY coordinate on a radius 1 circle. So we want to make that bigger, and we'll multiply the radius times sine and multiply the radius times cosine. Now, what we're also doing here is I'm using the execution index as the degrees input. So that means we're not going to do a full circle until we've moved 360 centimeters, which is going to make for a really drawn out spiral. We want it to be tighter than that. So I'm going to add another variable here called tightness. And so to increase the rate at which our degrees change, we're going to multiply execution index by tightness and then feed that into sine and cosine. All right, so then we add those to the X and Y, or Y and Z coordinates. We've got all of the Transform stuff already locked in. Now if we come back here, we just need to add, I'll add a couple variables. Radius, and we'll make that 10. Toss that in, and then we'll, I won't even turn that into a variable. Okay, so as you can see now, I'm going to pause the timeline so we can see this in effect here. As we increase the radius, oops, that was too much. Lost my play button. Okay, as we increase the tightness, we get that cool little spiral. I do want to make this the same color as everything else. Yeah, nailed it. Okay, so now we get our fancy little spiral. But I disabled everything else, so we're not seeing those effects. I want to do something else though. I want it to kind of get bigger, almost like that shockwave is evaporating, moving out. And so we can do that by doing something similar to position, but now with the particle velocity. So here, where we have our same logic for positioning stuff, it also works for velocity. So I'm going to create a new float just called speed so we can make that a little bit variable. And we'll take these guys, but instead of multiplying it by radius, whoops, instead of multiplying it by radius, we're going to multiply these by speed. So that way they'll gently expand. Now I don't want this wave moving forward, so I'm going to keep the x velocity at 0. But we do need to transform this from local to simulation. Let me wire that up to velocity. Click apply, and now when we come over here, we add a little bit of velocity, and you can hopefully see them kind of expanding. But to make it even cooler, curl noise, yeah. So we'll add some curl noise to this, and now it like distorts and gets all wobbly. Pretty cool. Can you guys see that okay? Yeah. So then if we go back and turn everything on, since we're soloed out here, now we can get the whole effect. Pretty cool. Any questions? We good? Yeah.
So for those graph modules, they exclusively you actually don't.
There's a node where you can do your own custom HLSL.
Oh.
The only downside to using custom nodes, it's the same thing with the material graph in Unreal, is if you write your own custom nodes, then you don't get any of the compiler folding. And so you have a risk of it being less efficient. So like the compiler is, from my experience, pretty smart. And so it'll notice, hey, this exact same equation was done over here and over here. Let's just reuse it. Whereas if you're writing custom code, you lose that. Yeah. All right, I think it's a good place to stop. We can keep going, but it gets the gist. We got the spiral. That was the thing Thomas wanted most. And we still have battery life. Look at that. Sure. Yeah. You certainly could. So with that plague I showed at the very beginning, the way you do, you've got a couple ways you could do it though, but basically it's spawning decals. So it's not even spawning a mesh or a sprite, it's spawning a decal, which is a newer thing that they've recently added. You could also spawn a mesh. Like realistically, you'd probably do a few things, right? You'd have an impact effect where some debris shoots out, and then a decal is going to be the easiest thing to spawn and not have to worry about Z fighting, right? Where stuff shares the same coordinate. But yeah, so it could do that. If you wanted to make the hit more reactive based on the surface it's hitting, then you would need some outside code. So in the code where we're doing the line trace here at the very beginning, this is the line trace that figures out the distance that then feeds it into the system. That's where you would look and get information about the surface you hit. And if you wanted, you could feed that back into the particle system, or you could spawn a totally different particle system. There's 101 ways you could do it. Yeah, yeah, yeah. And the cool thing about like a magnetic one is you could apply a attractive force in the Niagara system. And so you could supply that force with just a random world coordinate, and then all the particles within a certain radius will gravitate towards that. So you could have the initial blast that pushes the shell pieces out, and then if they're not pushed out far enough, they slowly come back and like reassemble. Like you could do all sorts of cool stuff. But that's where I think Niagara is most exciting. Just the crazy things you can do. So the engine has buffers, like buffers for color, buffers for metallic, and all those things. You can sample those in Niagara. So you could sample the wall color and texture and then have debris come off that is the right property. So it actually looks like chunks of wood, chunks of metal, and you don't even have to have a surface-specific system at all. It's just like, hey, whatever was on screen right at that location, we're going to sample and copy and do stuff with. It's really cool. Yes, with a lot of disclaimers. So I didn't get into it, but there are CPU particles and GPU particles. CPU particles, you can have far fewer in a scene. Like once you hit 10,000, your frame rate drops, whereas GPU particles, you can have millions. The problem with GPU particles, though, is it's really hard to get data out. So most of that type of stuff is just off the table for GPU particles. If you have CPU particles, there is a group in here. You can add another stage called event handler. And that's where only CPU particles can do this, but they can send data events out. So that can go to Blueprint or C++. You can do whatever you want with. You can use that logic to then spawn other particles. So a really good example is a firework. You might have your initial particle that's the rocket shooting up, and then at its location where it chooses to self-destruct, it then fires an event that says, hey, I've died. And then other particle emitters are listening for that, and they explode. But all of those have to be CPU particles. So the dirty trick is a lot of times you'll do really fancy visual stuff with GPU particles, and then you'll have some invisible CPU particles that are driving event-based logic. So in Dirty Dirty Pirates, the playfield gets ridiculously bloody. Sometimes the entire field is bloody, and that is CPU particles communicating to Blueprint, which is then spawning blood decals with a lot of management logic to make sure there aren't too many in one area. Any other questions? Wonderful. Okay. Well, thanks, everybody. Thanks for coming.